Sure.
So, should probably do a send mail to Michelle that said, Jim said we have this day.
Sure.
Just, it's like, John asked, luckily, you answered the optimum question,
Well,
but, sort of, I should have known that, all that.
Well-
But you kind of knew some of it.
well, right, and he's done this before. This is probably at least like the third time.
No, because he does this, and he'll do it again about 2.5 months from now.
Right.
Next forward bill. So
Right.
That's not the problem, is that it reminded me that I'm not tracking it.
Right.
And we should be looking at what are some options, showing things where the things.
You're right, and some of the stuff that's coming up like Bolex and like, whoa.
Yeah. Again, I'm not quite sure how many projects we're supposed to have.
Well, until they say no more.
That's what I figured.
Yeah. So you still got a few minutes whenever you're.
No, it's good.
Well, what are we doing there?
I'm just finalizing there's just 2 more slides. I'll just cut
Okay.
out to the results and.
We'll finish up and. I just put up the test pattern, so we're actually I should mute because we're. like this. We're live. Just get ready.
Mhm.
All right, so welcome everybody to our second to the last TWED of the fall 2015 season. Today we've got Amar Viswanathan, which is going to be talking about what he did last summer, his most recent research, partly at IBM and partly here after returning.
Yeah.
All right. Just a couple logistical reminders. We are streaming right now, so keep that in mind with your questions and statements and assertions. This is going to be recorded and will be available via the TWED website. For those watching in the ether and here, remember we've got the final TWED of the fall 2015 next Monday. It's our lightning talks. Get those 2-minute talks ready to go without further ado.
Yeah.
And you may hear my thing go off when the pizzas arrive. So,
All right.
so
All right.
just hit.
So present.
No, well, get them present mode and then.
It should be fine, right?
Let's go.
It should be fine. Are you guys able to see
Yes,
it?
we're good. You are good to go.
All right. Hi,
We are.
everybody.
Don't go back and do the monitor and not the.
No, it is a monitor. It is monitor. See whether that's what you're seeing.
Just give us-
Are you guys able to see it?
Right. We have to wait for that. Perfect.
Is that all right?
Yep.
Okay. Well, hi, everybody. Thank you for being here, to all of you. I know it's really late, and I'll try keeping this short as well. The title of this talk is Pragmatic Query Reformulation. We'll go, we'll go into the definitions very shortly on knowledge graphs. I work with. This is partly the work that I did with Geeth from IBM and with Professor Hendler, and this is part of the NSCTA project at ARL. And let's actually go and see what this is all about. All right. So before getting into what pragmatic reformulation is, obviously here we are at TWC and we're going to use RDF graphs. Although I'm not calling it RDF graphs, much more cooler to call them knowledge graphs these days. So you have different kinds of knowledge graphs. When somebody says RDF graph, it's very simple. But these days, people have, when they say knowledge graphs, they mean a variety of things. So things like NEL. NEL is basically a never-ending language learner. Keeps looking for, keeps reading the web, collecting knowledge day in and day out. Yago and DBpedia, most of you are familiar here with. And all these are called knowledge graphs. Now, you know that they encode information, concepts, relationships, and the amount is staggering, right? Any simple knowledge graph would have billions of entities. Search results obviously are systems. Today's search systems, right? They're able to handle all these results. The moment you fire in a query, it is very easy to see query that's huge. The volume of queries that can be written is huge, and search systems are very capable of handling them also. But the issue is that user, right? The user has, with all the information that is available, it's the user who makes the choice and says, okay, this is the information that I need. This is the information that I queried for. And let's say if that's not the case, let's say if his search query does not satisfy the requirement, what does he do? He goes back, repeats the process again till he finds what he's looking for. But the onus is on him to take all the results that's available, finally, compile them together, and figure out whether they satisfied his need or not. And obviously, it has been successful for quite a long time, and we all know how it's done. The question is, can search be improved? Question 1: can search be improved? At the end of this slide, can it be better? And then, does this model of search work in all conditions? Right? When you're using the web, it's all right. It's perfectly all right to have all the results given to you when you have the system to handle it. But is that the case? Is that the same case in all situations? Now, what about this situation? In a situation where your bandwidth is constrained, essentially, the situation that was presented to us is a network, a network of data, a knowledge network, which has different kinds of data, not just text, audio, video, transcripts. But the issue is that its bandwidth is constrained. There are some edges where the bandwidth is constrained because people um, assume that people don't have the amount of bandwidth that we have. They might be it might be a field agent who's querying data on his mobile network, and maybe the bandwidth is lesser, or any other situation. So in such cases, let's say you have a query and you have a humongous amount of results. Do you think it's appropriate to send all the results to this agent who's having just a mobile phone to look at these results? Do you think it is all right to do that? But then again, he does still need the information, right? He does all the search results that the system gives out. He needs that information because once he queries, he needs that information to either make certain decisions. So what do you do then, right? So this brings us to the motivation of this work, which will hopefully in some form would be what I would do as my thesis. So the background is really bad here. All right. So the motivation here is, can we have a system that can understand the user preferences? Imagine if obviously search today is agnostic, even though Google does some kind of user preference modeling. The modeling is not tailored to a specific user. It's more like a global optimization rather than a single user optimization. You're put into a set or batch of users who have a similar search pattern or activity, right? So, but in this case, each agent can be different, right? Each agent would have different requirements. Some people might be in different. A simple example would be somebody being in different geographical locations. The kind of data that you'd want to serve to them is completely different. The other issue would be, yes, each one would have a different preference. The preference would basically be, for example, domain expertise. You don't want. That's a simple example of a preference. Then once he asks a query, right? Can this system interpret the query in an intelligent manner? Now, a lot of work has been done in query interpretation, from the natural language processing side. Now, we're not going into that part where we say, oh, we're going to tackle the problem of query understanding in the philosophical sense. But can you interpret this query in a much more effective, constrained, and an intelligent way so that you can better serve them with results? The other thing is, when you give answers, when you decide to give these results, is there a better way I can provide him with additional hypotheses such that the next time when he makes a query, he understands what's already present out there. Out there is out in the data. Now, finally, the other question that we forget is, yes, you can do all of it, but how much do you want to provide to this person? And then how long it's going to take, because you have the bandwidth. You've already decided there's a bandwidth. How long are you going to take? So this is our motivation. So we come to the challenge. So we define something as what is called as pragmatic context. Pragmatic context is just a fancy term in this case, but it encompasses certain things. One is a user preference. Two is domain expertise. Basic domain. Let's say, just for example, there's a new user who's an agent who just comes into the network. We know that his expertise is on a certain set of subjects. That's a simple domain expertise. The other thing is the location in which he's present, in one geographical location, coordinates where he's present, and then networks from where the data comes from. So that's all that is going to be pragmatic context. All right. Then, now that you have the pragmatic context, what do? You have this user query. You still want to be able to query the network, right? Like you're talking about the situation where the system has to interpret the query properly. So you don't want this person to come and type in a long Sparkle query, for example, on a mobile phone. You'd rather want him to just say have a few keywords or just type in a short sentence perhaps. So you have this user query form. You want to translate that into a structured query form. Essentially, that structured query form which aligns with your the language that the database speaks, right? So that once you do this, you also need to preserve the semantics of the original query. You don't want to translate the user query into something else. You want to make sure that you preserve the semantics of the query as much as possible when you translate this. And finally, query reformulation. Why do we need query reformulation? I'll talk about it again, but still, what is query reformulation in context and why is this a challenge here? Okay, so when you translate your user query to a structured form, not always it can get translated into the right, I have a requirement, it doesn't always get translated into the right form in Sparkle, right? So what you do is instead of doing that, because you know it's not accurate, you say that you intelligently provide additional queries. You just rewrite or reformulate the queries by taking in specific terms and concepts in the query, aligning it with your schema, and then saying, okay, as an example, select all sports people, select all tennis players playing a match today. Well, the system does not have data about tennis players, but it knows that there are a lot of people who are playing, some other kind of ball sports. So a simple reformulation could say, okay, select all sports persons playing today. Now, what the system is trying to do is the system is trying to guess what the user could have meant, and that guess is actually a reformulated query. That's what is called as reformulation here. So but it has to be in context, right? Now, the reason I give you this example is when somebody is asking about tennis, obviously he doesn't want to know about any other sport playing. It can be better something related to tennis, or just say, okay, I don't have anything related to tennis, which is why you need reformulation and context. All right, and then finally, once you have these reformulated queries, you'll have to rank them in some order, right? Because you want to send them over a low bandwidth, so you want to rank them in some order. So what are the confidence metrics? How do you pick one query over the other? So what kind of measures that you use? And finally, the most important thing is, what you've said all this, what are the kind of benchmarks that you want to evaluate your system? That is also a challenge, and you'll see why it's a challenge. So why query reformulation? In an ideal world, everybody having data, in an ideal world, the perfect data source, you could just go query it. It would give you the right answers. There is a system which understands your query completely, translates to that data source, gets you the right information. But however, like I said, we have different kinds of data sources everywhere. Simple example, you have NEL, DBpedia and Yago, for example. The schema is completely different, right? So each new knowledge source that comes in has its own schema. Yes, there are mechanisms to integrate all of them, but at the end of the day, they're all different data sources with their own schema. So the schema is not uniform. Now, incomplete and inconsistent data. That's always an issue, right? With DBpedia, for example, the way DBpedia's data is filled in DBpedia, there is bound to be inconsistent data. A data which might be present in the schema might not be present as an instance, whereas an instance might generate new data for which there's no schema definition yet. So there's always this game that we're trying to play as to, whether you want. There's always an issue of data which is always incomplete all the time. So that's one. Complex querying. Now, how many times would you see users issuing queries in DBpedia that involve more than, say, 6 or 7 triple patterns? And what kind of triple patterns are there? So somebody comes and asks you a question and say, hey, can you find me people who have acted in movies? in movies directed by a particular director. That's a simple query. But then somebody comes and asks you a query saying, hey, can you find me people who have acted in movies with a particular star and a particular director, and they have certain other relationships. Now, the moment you have a query like that, even an expert user sometimes does not, get the query right at the first attempt. So obviously, what the user intends is not translated to the query the first time, or it doesn't always get translated. And part of it is due to the complex schema, because it takes a while for the user to get used to the schema and then compose a correct query. And finally, something that's allied to this is less adaptive search interfaces. It would be better if your search interface says, hey, I think this query that you have is wrong. Obviously, we don't have that, but perhaps it could say, hey, here is a query that you have issued. I'm not sure whether this is right. Perhaps this is the right way you should form it. Perhaps this is what you meant. And if that system could understand what this user, has some understanding of the user context, obviously it would give a much better suggestion. So
Do we have any formal substantiation for particularly those last two assertions? Number one, the sort of the formal answer to the question you posed is how often would you submit a query to DBpedia and have it be?
So there was a study actually. There was a study made by. I'll actually. Interesting that I haven't referred to it here, but the paper that we talk about has a study which refers to the kinds of queries that DBpedia has been getting over a period of time, and the maximum number of query patterns that they've seen is 15 query patterns. Okay, 15 triple patterns from the query, and the most number of triple patterns are between 1 and 6. The most number of triple patterns are between 1 and 6, and the most you can do is just 15. And that's all there is. That's all they've done. And these are basically star queries, like select star with certain properties. Sure. These are not even
discovery kind of queries.
Discovery kind of queries. These are not even complex queries.
So that's from the DBpedia.
That's from the DBpedia standpoint. So that's one thing. And about adaptive search interfaces, there's a recent study by Dan Tunton who's talked about the need for systems that can adapt to users much better, rather than when you go to Google, you just have this simple search box and it gives you a set of results, and you have to make the choice of the right answer. Well, that's obviously easy when in the situation that we are in, perhaps in an academic environment, perhaps it's easier that we can take in all the results and find out the right answer. But with the kind of networks here, it would be better if we, give the user something more than just the results. So that's the reason why I say that search interfaces are not adaptive. So how do we tackle this? We'll just get into the system because that's more easier, and then I'll explain what part is done and what we're trying to do. So the idea is that a user issues a query to the system. This user can be in a constrained network. The system comes back with a set of results, obviously, for this query, but also says, hey, here, this is the query that you asked. Here are additional queries. These may be queries, perhaps, these may be something like, oh, perhaps you meant this, or these may be queries like, this is a query that you have asked. Perhaps you may also be interested in the other query, which I'm sending you. So now, how many such queries do you want to send? How do you select those queries, right? A pretty simple system. User enters a user query. It goes through what is known as query relaxation. There's a difference between relaxation and reformulation, obviously. This entire pipeline here actually reformulates. By relaxation, you're just relaxing the query. You're using the schema present in the query, to relax the query to its all possible combinations, and we'll show you what all possible combinations. And then once you have all the possible combinations, you want to reduce them, right? Because you're sending them to this user. You want to reduce them. So that's what you use different techniques to reduce them. You use semantic similarities, then you use data awareness, and which we'll talk about, and then finally there's context awareness, which is what we would want to do soon. Then finally, once you get a set of queries, you want to rank those queries by their similarity to the original query that he has, and then once you have that, it can be either a top K based on the network bandwidth. The K, then the number of reformulations that you want to send is basically top K, and this top K is determined by his network bandwidth. And the background data set that we use for this is basically a knowledge graph. For this task, what we try to do is we build this knowledge graph out of the information extraction that's done by Professor Hangji. She has, you know, we've converted about 8 billion documents currently to what this is basically is that you have a set of newswires. The newswires talk about people, places, events, relationships between people, different events, perhaps the same event, and all the connections. So she's actually extracted the entities, which may be organizations, people, places, things like that. Then she's also extracted events, which is basically interactions between these entities. And then finally, she's also extracted relationships between entities. It can be relationships between organization, which can be, an organization is a sub-organization. It can be another kind of a relationship where a particular person works for an organization. For example, let's say Amar works at RPI. So there's an entity, Amar, who's a person, and RPI is an entity, which is an organization, right? And events, obviously there are also events. Events are basically, let's say there is an attack event happening somewhere. So the Paris attacks have happened. So that's an actual event that has happened. The entities that are affected is Paris, which is basically the target in this case. There are terrorists who are the entities attacking this. We right now we don't know the terrorists, but let's say terrorists just are the people who attack. So these are the kind of information that's extracted. Now the problem with this is that it was just extracted and put on XML documents, for example. And what we did is that we said, hey, we sort of know some details about what you've extracted. We know that the recall, precision and recall is very high with these documents, but obviously it's lost some of its meaning because when it's in disparate sources, it's just event only, entity only, relation only, doesn't make sense. We have the document IDs from which you have extracted this. Let us combine all of them together, make a graph. And in this case, we just built an RDF graph. Now, what this does, just a small thing, what it does is that if you just had an XML document, it would have gone to an INRI system, and all you could do is keyword queries, right? You would just say, if you wanted to find events, you'd say events, Paris, something. But once you've converted it into a knowledge graph, you could actually query something like, tell me the person whose organization was involved in an attack in Paris at such a date, because you have date information as well. So you see what it does. You have a relationship which is basically a person who's part of an organization, which the organization participates in an attack in a location at a particular date. So you're able to compose many relationships together and build a query. And now this would be almost similar to the kind of information that agents would have with them. Obviously, they'd have heterogeneous information, like they might have video, they might have images. But the notion is that at some point, your knowledge graph would be able to support such kind of information. And so this is one test that we have right now. And because this data is readily available, we decided to use this and see how we can, use this particular data set and see whether reformulation is a good way to go ahead or not. So what is the reformulation methodology here? Yeah. So basically, like I said, we've already talked about this. Query goes in through a reformulation step. One other thing, definition, obviously, if in case you want to read the paper, I can send you the paper. of course, till December 22nd, please don't share it because it's with www. But any SPARQL query can also be called as a conjunctive query. Basically, it's just a conjunction of triple patterns. The head of the query is what you're trying to select, and then so this query goes through query relaxation. We'll talk about how relaxation happens. Relaxation happens through a set of basic entailment rules. Now, these entailment rules, we have actually extended some rules that have already been, you know, created by people already. The specific work that we're doing is Hurtado's work in 2006, where he actually came up with the first set of rules for query relaxation. His work in turn is actually based on Terry Garland's work, which is the seminal work on query relaxation per se, wherein although the older work is basically on relational databases, Hurtado used the notion and built it for RDF-based databases. After you have query relaxation, basically, once a query goes through a query relaxation process, you just don't have a single query. Because it has been relaxed, you get a lot of queries based on the different concepts that are present in a particular query. So you need to reformulate these. You need to reduce the amount of queries by. Here we do a similarity matching first, and then we use what is known as data awareness. I know some of you might ask me the question, what about the user context and what about the other things that we're talking about, especially geographical coordinates and so on. That's the work that we're going to do later, and that would be another addition here, wherein you reduce the number of reformulations. Right now we have results for data awareness, and we built a similarity notion of a similarity matching algorithm, although that can also be extended. So that's all we're going to talk about. Relaxation rules, very simple. So basically, let's say you have a simple notion. The first 2-3 rules are pretty simple. Individual. Let's say there are 10 different kinds of individuals. Now I can be a student. 3 others can be students. You have Professor Jim is a professor. John is the director at IDEA. There are different kinds of people. So suppose somebody comes and says, "Hey, he comes with a query and says, give me all the people working in RPI, and these are the only people that you have." Obviously, one way to look at this is say that all these, student, director, professor, all are just subclasses of the class people, individuals. So now that's one relaxation. Similarly, you can have, on a similar notion, you can have a property relaxation as well. And then finally, you can have triple instance replacement and property instance value replacement. So let's say you're selecting a certain instance of a terrorist. You can have a different terrorist. Hey, let's say, give me this terrorist Saddam Hussein. Saddam Hussein not terrorist. Technically, he is a leader. But give me this terrorist Osama bin Laden in the data. Give me instances of Osama bin Laden in the data. The data might come back and say, hey, I don't have instances of Osama bin Laden. I know Osama bin Laden is of type terrorist. Do you want other terrorists, perhaps? You have triple relaxation, so on. You use these relaxations on the queries, and then the moment you use that on the input query that you have, you end up getting a set of relaxed queries, right? So these are the algorithms that I use. So basically what you do is you take these queries, run it through all these rules, you get a set of relaxed queries. The moment you get these relaxed queries, all you have to do is say, hey, I first want to see if there are a lot of similar queries. If there are a lot of similar queries, I don't want to use all of them together. Let me club them together to form a generic query. Then finally, you say, okay, the moment I've done with similar queries, there is one other thing. Although the schema might talk about terrorists present in a particular location, the data might not support that. Technically, the schema allows for terrorists present in a specific location, but what if the data present doesn't actually have anything related to that? Do you really want to do a schema-based reformulation at that point? Obviously, because even if you do a schema-based reformulation, it's going to return only an empty set, right? Because that particular query, which says, hey, select terrorists from a particular location, and if that location has no results at all, you don't want to reformulate that specific uh, part. So what you do is you say, okay, the moment I have this query, let me look for those instances where there is no data. Let me look at those reformulations which have reformulated queries which do not actually point at data which is present. And then the moment you do that, you reduce those queries as well. And then that's your query pattern reformulation. So that's what the data awareness is all about. This is the RDF Entailment Rules. So finally, we're going to talk about the kind of queries that we are using on ACE datasets, the evaluation that we're using. Right now that you have all these queries together, what do you do with them, and how many queries do you send? To answer the question of how many queries you want to send, we actually built. Oh, where's the match algorithm? Okay. So you see this match here. Match actually goes to another algorithm. The algorithm, what it does is it says it assume that it runs a similarity match. Basically, looks at how similar the once the queries are reduced and you have a set of queries, how similar are these queries to one another? And then finally, once you have a notion of their similarity to one another, you then look at how far they are away from the root query, and then based on that, compare your network bandwidth and say, okay, today my network bandwidth allows me only k queries, which is, let's say, 10 queries, for example, and send you those 10 queries. So now that we've done that, we'll just go to the ACE datasets. Now we talked about ACE datasets. What we've done here is that for the paper, we just took 75,000 documents because we wanted to run it on a simple set and see how it works. We didn't want the reformulation space to become really, so we just took 75,000 documents. We converted them, and the metric that we used was the top events that's present, the top event instances that is present in the dataset. In this case, it was attacks, and attacks are basically have a specific. And then we also took the top entity types. In this case, the top entity types were basically people and countries. So we decided to compose certain queries based on them. The idea of these queries, I mean, they look like random queries, obviously, because we still feel we have not had the best evaluation possible here. But the idea behind these queries is to create a form of query which is basically which can which is complex enough, which is not just a star query, which can handle at least more than 3 triple patterns. And then in this case, all the queries that you have here, at least the queries that I'm showing here, have 6 triple patterns. Like it requires 6 triple patterns. Once these queries are translated into Spartan, you at least need 6 triple patterns. And based on the study which we saw, we said, okay, we have, on an average, there are at least 6 triple patterns. Let's see if queries that have 6 triple patterns, how do they do? These are the number of results that you see. The moment they go through the system, for example, let us look at this query, all the people who are involved in attacks. What happens is that you get a set of reformulated queries. And the reformulated queries would look something like this. What basically it does is says, hey, all people who are involved in attacks. I do not know how they are involved in attacks. So what I'm going to do is I'm going to go back to the data and see how they are involved in these attacks. And then it says, hey, a person might be involved as an attacker in an attack. That's the closest that I get. A person then might be involved as a target of an attack, which has a similarity of 0.98. Then I see that a person can just be an part of a person can just be an attacker or a target. Now I say, okay, let's go to the attack. I see that attack is of two different kinds. One is a conflict and then another is a demonstrate. And it says, hey, if you didn't want something which is an attack, perhaps you said, perhaps can I show you a person who's a target in a demonstration?
What is it?
Well, the demonstrate is basically so A schema says that attack has conflict and demonstrate. The event attack, there are two sub-events for it, which can be, one is conflict and one is demonstrate. Demonstrate is basically a group of people together, and perhaps of a negative connotation, but well, that's just the schema. That's just how the schema is. It could be anything else as well. It's just something that's been extracted.
So here you're asking for people who are involved in attacks.
Correct.
But they can be involved in attacks as attacker or as target.
Correct.
So you want to find out.
So those are your top two reformulations, right?
Yeah.
It's still correct. It still says, okay, I'm going to give you something related to attack, because in this case your query is very precise here. Let's say if your query was just something like all people who are involved in an event. At that point, what it would come back to you is say that this would completely change and say individual, this would become a variable, and this triple would have all the different kinds of events. And then what happens is that you'd want to select the right event. Then every time then finally when you decide to select an event, the roles change. At this point, you're just seeing the fact where you've actually narrowed down on a person, you've narrowed down on an event type, and then you're trying to reformulate.
So the final one, the fifth one, is what is that saying?
Well, apparently in a demonstrate, when you don't know the role of an individual,
Yeah.
you just call him an entity.
Okay, so they're somehow involved, but they're not.
But you don't know what the system, the extracted
they're
system.
not being attacked. They're not.
The system doesn't know what they're doing. So, yeah, but that again, that just comes from it just comes from the data.
I guess that makes sense in the context of reducing or processing like news reports and that sort of thing. This person is somehow. They could be the subject of the shouting of a demonstration.
Yeah. So I mean, this can very easily be looked at as an agent saying, okay, can you give me people who are involved in this particular event? Maybe in his mind he thought this was an attack event, but perhaps that was not an attack. But in the larger context, it was just viewed as a demonstration, perhaps, whereas small skirmish happened between people. Or perhaps it's a much bigger thing where it's a conflict between two nations, and then that's the event he actually wanted. So the next reformulation here, obviously what we wanted the conflict to come up here, but the top 5 just looks like this, which is very
okay. So that was another question I had, was where I would expect to see sort of a symmetrical expansion of attack to demonstrating conflict, but what you're saying, you're showing the most.
Yeah, and there's a reason why that happens,
Okay.
and which is why the future work would target that similarity. When you say similar queries, when you say similar, when you want to rank these, which one do you, what is the first thing that you want to give preference to? Do you want to give, in a query like this, especially in a query like this, do you want to give preference to the event? Do you want to give preference to the role? Do you want to give preference to the people? So what's the similarity metric you want to use? How do you rank them? So that's still a problem that we are trying to tackle. Right now we say, okay, there are people who've been working on Sparkle query similarity. We just looked at and said, okay, here are two algorithms that we can use. One is just a simple string similarity on the particular entities that have been matched. Once, if you don't have a string similarity measure, what would you do? One possible angle that we are looking at right now is use the data available and sort of a conditional probability. But even to apply a conditional probability, you actually need to know which one to pick first, right? The order. I mean, once it boils down to that, different people might have different notions. So how do you want to enforce the order? Right now, what we're theorizing is that we're saying, okay, let us use the user preferences, let us use the coordinates, let us use them to enforce some order. Let us see if they give us some order on the ranking, and then does that give a better reformulation? And then once the next step after this is the kind of query where somebody comes and says, hey, can you tell me what kind of events Osama bin Laden is involved in? Now, in this case, you have a particular literal Osama bin Laden in the query, and you want to know the kind of events that he's been involved. The problem in this case, you see that it's very generic. You said people who are involved in attacks, so people would be instances of people. Osama bin Laden would also come in this, but in the next query, you have a very specific query where you say, I want only events involving Osama bin Laden. So what do you do then? So then, in that case, you already know that something is fixed, and then you know which order you'll have to target. In that case, the reformulations would just take the attack first, the event first, because you know that Osama bin Laden is fixed. The user has specified a particular literal.
But wouldn't somewhere down in the less similar options, wouldn't it be sort of, well, maybe we don't need Osama bin Laden, but Osama bin Laden's people. So that would be further on down,
yes.
Even though you've said literally Osama bin Laden.
Well,
maybe you mean Osama
well, I was
bin Laden.
coming to that. So we don't know how to term that, but that's a kind of reformulation that we're looking at. We're saying, I do not know Osama bin Laden. Perhaps Osama bin Laden is present in the data, perhaps he's not present. If he's not present, let me find other relationships that the term Osama bin Laden has, how it is related to other concepts nearby, and can we extract something from it? Do we show events that his son is involved in, or do we show events that the events that his organization is involved in? But in this case, you already know that it relates to attack. So it would be prudent to say, okay, let us see if the organization is involved in more number of attacks, or the sons are involved in more number of attacks. If let's find a balance and rank them. So that's the next problem. Although you can say, okay, you can use attacks and find some ordering scheme again. How do you do this ordering much better and dynamically? Because every time the user interacts with the system, he can change to another query, right? It can go to the organization Al Qaeda and quickly go to another, another terrorist, Zawahiri or somebody there, and then you want to see, because Zawahiri might be alive, and so there must be new data coming about him. So you want to move on in that direction rather than somebody who's already dead. So you start at some point. The idea is not just provide reformulation. The idea now suddenly becomes that you're not just giving the agent some results, you're also giving him some queries. But by that queries, you're also showing him how the layout of the data in some intelligent, constrained way, which we call pragmatic reformulation, by the way. So that's the idea behind the entire reformulation part here. So yeah.
Speaking of moving.
Yeah, moving on, and so obviously, even though we've submitted this, there are still questions on how better can we evaluate this. What is a much better way of evaluating this? What if there were geometric coordinates involved in the data? What if there's weather involved in the data? How do you compare? Similarity metrics change. Like if distances were involved, the way you measure things, something near to you is just by you just look at the distance metrics, you just see how close they are to you. If weather data is involved, what do you do then? If location, so the notion of similarity, we're trying to figure out that so that we'll have a much better evaluation set, not just saying, okay, these are 6 triple patterns. Right now, we are at the point where we say we take queries of the form star, composite, and interlinked queries, but you want to go more than that. So you just want to make sure that evaluation is fine here. And that's something that we're working on. And finally, we did some results on the Lehigh University benchmark baseline. They have a set of queries. This is also based on an earlier work, but in the Lehigh University, so the Lehigh University benchmark has a set of 20 queries. Turns out that the early reformulation algorithms use that benchmark to say that, hey, once you have this query and there are 0 results, instead of just giving you 0 results, let me give you some reformulated queries which can give you results. At least that gives you some results. So what we did was we took those queries, we ran it on the algorithms that we have, and say decided to see. So the baseline algorithm is the first algorithm that was proposed on the benchmarks. This is basically query relaxations. REL is the algorithm that we have, which basically does some kind of reformulations. REL plus DA is data awareness. Once you say that, okay, include this notion of data awareness, what happens? And finally, the number of reformulations that happen for your ACE datasets. What happens if the same queries that you have here, all these queries, these are the number of reformulations that happen on the baseline algorithm. Also, the baseline algorithm has not been defined for this particular data set, even though we just thought we'll try it to give some sense of what kind of reformulations that we are getting, to get some numbers of how less or more these reformulations are. And, you see that the addition of data awareness works, let's say all the data is present, then there is no need for a data awareness algorithm. It works really well only when sometimes there is no data present. So looking back, I think we would have to have, we perhaps done 2 or 3 more iterations or splits on the data to show how it performs on an average. That's something that we are targeting in the next conference, and hopefully the reviews also might come up with that. So that's about it, and yeah.
This was the slide that you did right before that.
Yeah, so it's
702.
Yeah, this is the final slide, and I think the future directions, at least at this point, is one, find a better method of evaluating your query reformulation. Once you decide on what numbers your query reformulations are, the next thing is define a similarity metric that works well in general. Given any kind of data, of course you have a constrained network, but given any splits of data, the similarity metric that you have chosen should work well. So your evaluation for your similarity metric becomes important as well. If you're using data availability and some sort of a conditional probability, how are you going to use that? What kind of conditional probability do you want to use? Do you want to look at the data completely? Do you want to just look at specific parts of data? Then how do you choose that specific part of the query that you want to tackle? For example, in this case, if a query is Osama bin Laden and events that he's involved in, we clearly know that all you have to worry is about the events, because in this case it's very simple. But what happens in a query where you have a very generalized query where just show me all instances of all people involved in all kinds of events? So then how do you walk? So for that, what we have decided is that we've built a reformulation graph. We just said, okay, here is a graph. Here are the possible reformulations of this graph. And then we've converted that into what is known as a reformulation graph. Added some similarity values to all the edges. And now this will go to one of our collaborators, which is Tom Laporta and PSU. he has an algorithm which takes in basically a strategy with all these probabilities and gives a best strategy when there is a network constraint. Given a network constraint, given this query graph, reformulation graph, which was basically coming from an input query from an agent, what is the best information that I can send first to this agent based on the network bandwidth? And so that's how this entire thing works. And
so we got plenty of time for questions. So let's thank Amar first. You gotta make it sound like there's 30 of us.
yeah.
Well, so Amar, what?
Can you explain how what you presented actually addresses the problem?
My assumption is that for limited bandwidth, the number that comes to us from, let's say you have an input query that is given to you. The input query also comes with saying, okay, if this input query can come to you with a reformulation graph, this is the number k that can. The way that I form my reformulations is just based on a reformulation graph and the top k reformulations that I can give to that reformulation graph. The k that comes, I have no clue of the k. I would assume that the k comes from the network, or the edge tells me that this k, there is some way to determine this k that goes into this algorithm. Am I being?
So are you saying that there's an association between the bandwidth required and the number of reformulations that need to be presented?
Well, that's the setting we have, right? Well, the setting is that the amount of data that the particular edge can, the particular user can take because of the network he's in is very less. So you have to tailor the results that you have in such a way, in an order, right? In an order to send to him. So which results do you pick first, and which reformulations do you pick first? Now, obviously, I can generate all possible reformulations. I can have a notion of ranked reformulations as well. But the number of reformulations or the number of reformulation graphs that I want to send comes from somebody telling me, oh no, this network is constrained and this is the amount of information that it can take. At some point, it may be the case that the network can take more information as well. So in that case, you then adapt your system and say, okay, the k has changed, so maybe I'll give in more number of reformulations.
So what you're saying is, due to this assumption that there are network constraints, you're incentivized to have the most likely, the most reasonable reformulation.
Yeah.
So you want to choose some limited set of the possible reformulations.
Correct.
And you want to order them in a sensible way.
Yeah. And that's where the ordering algorithm becomes more important, right? The similarity matching. Otherwise, you could just have a query similarity algorithm. If there was no network bandwidth, if it was just a situation where you want to show 10 reformulations, then you could just rank the queries based on a simple similarity metric and
every
show.
Sparkle query I give it, I'm actually doing 50 of them.
Yeah.
And and I don't care.
Yeah.
But what you're saying, well, the assumption is you do care.
Yes.
I was waiting for pizza. Where we talked about bandwidth.
Yeah, but one other thing that you should note here is that the results by themselves are not ranked. Obviously, at some point, you would have to look at the way in which you serve those results as well. What we're talking about is reformulation queries which are ranked. But what about the results by themselves? We're just taking it off a Virtuoso source or Jenna, right? You'd want to do something to that as well at some point.
So I had a question. So there are practical implications.
Should I leave a message for
We
her?
often build these portals where a value proposition is that we're exposing the Sparkle. We're not just building this knowledge graph.
Mm-hmm.
We're not just providing these various canned reports and
Correct.
whatever.
Sorry, what was that? Could you repeat that?
But we also are presenting this Sparkle endpoint, so you can present your own query.
Correct.
Okay, which is
So
only
exchange what for no charge?
got, the RDF nerds on the other end, writing Sparkle queries. Okay?
So what
But
are
it's potentially hugely.
Okay, so
If we
go back to the beginning of
So
the
what
message.
I've not talked
What's
about
the
in this
beginning of the
talk,
message?
or specifically, is something that we've done to the user interface. We have actually built a user interface which takes in the query that you write, matches it to the concepts, builds a faceted schema, and then that facet allows you to,
Okay, I will let her know that that is an option.
all
and
these
see what
What are
she
you
can
using on-
want to do.
all these things are
Right,
basically
thank you.
facets. You just have, in this case, you would have 3 facets generated, and you could just compose your query with those facets. And each time you generate a facet, the reformulations would come below that facet, wherein you can click on the reformulation. The reformulation might, lead to the same set of facets being generated, or based on the navigation, you might end up having newer facets again. So we have built a user interface that adapts.
So
Technically, the idea is that he doesn't have to write a Sparkle query, but that's something. I mean, that's something the user interface test, or evaluating a faceted interface, is something which I've not done, or which I wasn't sure of putting it out there yet, until I was really sure that this is the way that I evaluate this, which is what we were talking about. Yeah, sorry.
Now that you mentioned the user interface, I was wondering about how you pragmatic context in determining what is pragmatic to a user.
Yeah.
But would that be something you could integrate into the user interface then? Like if the user could say here are my 3 facets, and I want my query is for all people who are involved in attacks, but
Correct.
you could decide I want them involved as the attacker system name, or I don't care if they're the attacker, but I want to make sure it's an individual.
Yeah. So the idea right now, what we've toyed around with, is that we look at the interaction patterns. We just picked up ideas from everywhere, looking at how people work with building Sparkle queries interfaces, and then we said, okay, what you could do is give the user a focal facet, focus facet, for example. Let's say once he's given a query, and then the system is unable to figure out what his focus is, we allow the user to change the focus. And then the generated reformulations are aligned to that focus. For example, in this case, if all the user cared about is the attack. But then again, that's just something that you give to the user. Whether it's going to be put into the system, whether it's required or not, is something that we'll have to carefully evaluate. There might be it might not be required at all for all with the reformulations that you already have, or maybe somebody is just trying to understand what's present, so he just wants to understand the particular thing without without writing harder queries over it. But the reason I've not put a lot of that here is because we want to be sure about the implementation one. We want to be sure about how we're going to present it and say, okay, this is how it's going to work, and we want to be sure how it's going to be evaluated or how people are going to look at it. These are not just users who don't know the data. Also, these are users who might also have an understanding of the data. So that also changes the system.
Any other questions? I could probably think of a lot, but I won't. It's after 8, so thanks again, Amar. Remember, everybody, to if you haven't already, signed up for those lightning talks. There you go.
Education.
Thank you.
We stop.